Okay, let's begin again. So in this video, we will be doing simultaneous differential equations of the form dx by p, dy by q, dz by r. I have told you that this one represents actually simultaneous differential equations, these two. And I have shown you how this is being converted into this. So let me start with this. If you have a differential equation of the form dx by p, dy by q, dz by r, this represents simultaneous differential equations. And I have said that there are 4 rules to solve such type of equations. See, rule 1, for solving dx by p, dy by q, dz by r, where this p, q, r are functions of x, y, z. Okay. Now, how to solve this equation? We have seen that for simultaneous linear differential equation, say you have dx plus y equal to 5x plus dy equal to sine x t. So how you are doing it? You are eliminating first either x or y. You are finding x first, then y, or first y and then x. So you are finding 2 solutions at least. Okay. Here, how to find the two solutions? See, what is the rule? Rule 1 says that if we will choose any 2 fractions of any 2 fractions, you have one fraction dx by p equal dy by q. These are 2 fractions. If you choose any 2 fractions of 1, and in these 2 fractions, see, this is with respect to x and this is with respect to y. If in these 2 fractions the variable z is absent, if it is absent, there is nothing to worry about. We can use the usual methods. Or if it is present but it cancels out, then still we don't have anything to worry about. So rule 1 says that if one of the variables, taking any 2 fractions of this 1, if one of the variable is either absent or cancels out, then a solution can be obtained by usual methods. Usual methods means which you have already familiar with in 12th. Okay. If you choose any 2 fractions, say these 2 fractions are you choosing dy by q equal dz by r, then you see x should not be there. Either it should be absent or it should cancel out. Okay, you can find a solution. This solution is known as u and this solution is known as v. And the u and v together represents the solution of this simultaneous differential equation. You may choose x and z also, then y must not be there or it must cancel out. We can have a solution. This is the first one. Okay, we will take 2 rules together. You have 4 rules, we are taking 2 together. This was rule 1. Rule 2. Okay, what is rule 2? For solving dx by p equal dy by q equal dz by r. This is always 1. See, suppose that we are taking any 2 fractions. We have taken any 2 fractions dx by p, dy by q, and suppose that one of the variable is either absent or cancels out and we are able to find a solution, say u. Okay, let me suppose that we are not able to choose 2 more fractions. Say we are not able to choose y and z, and then dx and dz, dy and dz, dx, and we are not able to choose any 2 fractions such that we may apply rule 1. Then what is being done is that you are already familiar with one solution. Then second solution is obtained with the help of this solution. We are using this solution to get another solution. Okay, this is the rule 2. Say, rule 2 says if one of the solution is possible by using rule 1 and another solution is not possible. Then we use, to get the solution, second solution, we use rule 1 or solution 1 to obtain second solution. Got it? We are able to find, take any two fractions, we are able to find one solution, and second solution is not possible by using rule 1. Then the solution which we have already obtained is used to find another solution. This is rule 2. Let me take questions. You will understand with the help of examples. See, let me suppose that I have taken dx upon x square, dy upon y square equal dz upon x square z square. This is one. Dx upon p, dy by q, dz by r. This is p, this is q, this is r. Let me take these two fractions. See, taking first two fractions of 1 together, we will get, what we will get? Dx by x square equal dy by y square, means x raised power minus 2 dx minus y raised power minus 2 dy is equal to 0. Now integrate this. I will get x raised power minus 1. Okay, this is minus because I have taken it over here. Minus y raised power minus 1. See, x raised power minus 1 by minus 1. Y raised power minus 1 by minus 1. You know x raised power, integration of x raised power n. It is x raised power n plus 1 by n plus 1. So it is x raised power minus 2 over here. So x raised power minus 1 by minus 1 minus y raised power minus 1 by is equal to a constant integration which is c1. So you have 1 by y minus 1 by x is equal to c1. This is u. This is u x y z. Z is not there, but this is u x y z. This is the first solution, right? So I have taken any two fractions. First two fractions, I have got a solution which is u. I have to find one more solution. Now, if I will choose dy and dz, see, z square is okay with respect to z, okay. A y square is okay, but x square cannot be taken, okay. So what I will choose first and third fraction together, because x square will cancel out, one of the variable will cancel out, and we can find the solution. So taking first and third fraction of 1 together, we will get dx upon x square equal dz upon x square z square. Okay, so x square cancel out. This gives us dx minus z raised power minus 2 dz is equal to 0. Now let me integrate. I will get x minus plus 1 by z equal to c2. This is another solution. Okay, so c1 and c2 or u and v. If this is v, first one was u, then u and v, or u is equal to c1. You know this first one was u. If it is, suppose that it is u and it is suppose that this is v, then u and v together gives the solution, or c1 c2, let me write, okay, c1 and c2 together gives the complete solution. Okay, for simultaneous equations you have to find two solutions, x and y. You are getting two solutions in terms of u and v. Let me take one more example. X dx y square z equal dy by x z dz by y square. x dx y square z equal dy by xz equal dz by y square. This is 1 as usual. This is dx upon p. You can put it as dx upon y square z by x. Okay, dx by p, dy by q, dz by r. Now, you see this is very easy. Simply, if you take first and second fraction together, this is x, sorry, dx upon p, dy by q, dz by r. This is the question. Now, if you take first and second together, rule one is saying that if you take any two fractions of 1 together, then one of the variable, third variable is z, is either absent or cancels out. See, this cancels out. So, taking first and second fraction of 1 together, we will have x dx by y square z equal dy upon xz. So taking any two fractions of 1 together, and if one of the variable is either absent or cancels out, then a solution can be obtained by usual methods. What is the usual method? This x into x, x square dx minus y square dy equal 0. Okay. Now let me integrate it. X cube by 3 minus y cube by 3 equals c1 by 3, or x cube minus y cube equals c1. This is first solution. X cube minus y cube equals c1, or u equals c1. Okay, you can represent as u. Okay, or likewise x cube minus y cube equals c1. There is no nothing to worry about if you will write it in this form only. You don't need to change it in terms of u and v. I will suppose that this is u. Okay, or this x cube minus y cube equals c1. This is the first solution. Now second solution. See again, you cannot take these two together. Okay, y square will go here, z will go here. What about x? You cannot do it. But you can always choose first and third fraction together, because y square will cancel out, x is there, z will go there. So let me take first and third fraction of 1 together. Taking first and third fraction of 1 together, we will get x dx upon y square z dx upon y square. Now rule 1 says if one of the variables, that is y is either absent or cancels out, then a solution can be obtained by usual method. So x dx equals z dy minus z dz equals 0. So integrate it. X square by 2 z square by 2 equals c2 by 2. This is another solution. So c1 and c2 together gives the general solution. Fine. This is very easy method. You can do it. Okay. Now let me take one more question. You may have dx by x, dy by y, dz by z. I will not solve it. Let me explain it here. You can choose any two fractions. See, if you take these two fractions, there is nothing to worry about. One of the variables is absent. This is log x, this is log y. You will get x by y equals c1. You can choose these two, y by z, or you can choose these two. But you have to take only two solutions. Okay. This is again the same question which you had somebody had asked me. If y1 is a solution, y2 is a solution, then c1 y1 plus c2 y2. Is there third solution also? You see, you have third solution, but you have to take two solutions only. You will see it yourself why we are taking two solutions. So concept of linear dependence and linear independence comes into picture here, as well as in first question when you asked me when y1 and y2 are a solution, then why c1 y1 plus c2 y2 is the solution. Same is the case with here. Same reply to your query, but then read the book. Okay. You can have any question now. So, okay, let me take some other question. Question 2 is, say I have dx upon, okay, let me take z, dy upon minus z, dz upon z square into and x plus y. Okay, let me take x plus y. Okay, okay, whole square. See, this is 1. Now, obviously, if you take first and second fraction together, you will get a solution because one of the variables is either absent, it is not absent, but cancels out. You will have a solution that x plus y. But you cannot take any two fractions now. See, you cannot take this and this because, okay, z will be here, but you have x plus y whole square here. What you will do? Similarly, you cannot take this and this. This is rule second, which says that if first solution is possible by using rule 1. Rule 1 is that any two fractions taken, any two fractions of 1, you can have a solution. This is possible. But another solution is not possible. We are not able to take any other two fractions. So what is to be done? The solution which will be obtained in the first case is to be used. Okay. See, taking first two fractions together, taking first two fractions together, we will have dx by z, dy by minus z. Z and z cancels out. This is dx plus dy equals c1. Sorry, which is 0. Dx plus dy means x plus integrated x plus y equal c1. This is a solution. Fine. Now, I will use this x plus y because I have x plus y over here. This is a constant. So, now you can choose any two fractions. You can choose y and z, dy and dz, or dx and dz. Doesn't matter. Okay. So, taking, this is a solution which is to be used. Okay. Taking first and last, you can take second and last, don't worry. First and third fraction of 1 together, you will have dx by z, dz upon z square x plus y whole square. Let me suppose that this is 2. Okay. Okay. Now, let me use this 2 in this. Okay. Or dx by z equal dz upon z square plus c1 square by 2. Because x plus y is c1. So, I have chosen x plus y. Now, let me try to solve it. This is dx. Dx equals z dz upon z square plus c1 square. Now, this is the function. Its derivative is 2z. So, let me write it as 1 by 2, 2z dz upon z square plus c1 square. Now, let me integrate it. I will get x equal 1 by 2 log of z square plus c1 square plus some constant integration c2. Now, what is c1? You know, your c1, x plus y is equal to c1. This is your first solution, okay? I will use that. So, x is a minus log of under root of, this is half z square plus c1 square x plus y whole square is equal to c2. This is another solution. This is the first solution. This is the second solution. So, c1 and c2 together gives the complete solution. Right? c1 comma c2 together gives the complete solution. Complete integral or complete solution. Okay? What I have done, this is rule second. Taking any two fractions of 1 together, if we are able to find a solution, and in this case we are able to find a solution which is given by x plus y equals c1. And suppose that another solution is not possible by choosing rule 1. Then the solution which is already obtained, which has been obtained, is used, and I have used that solution, that x plus y is c1 constant, and later I have to substitute back this value of the constant so that my solution is in terms of x, y, and z. I have said that first solution is represented by u, x, y, z, and second is given by v, x, y, z, because your p, q, r are functions of x, y, and z. Okay, you have got two solutions. Next one. Dx upon y, dy by x, dz upon xy z square x minus y, x square minus y square. Okay, this is one. Dx upon y, dy upon x, dz upon xy square x square minus y square. So this is dx upon p, dy by q, dz by r. Now choosing first and second fraction together, I can have a solution, but no solution is possible by taking second and third or first and third. Okay, this is rule second. Remember it. Now taking first and second fraction together, choosing first two fractions of 1, we'll have dx by y, dy by x, means x dx minus y dy equals 0, which gives us x square by 2 minus y square by 2 equals c1 by 2. So x square minus y square equals c1. This is my first solution. Okay. Now I don't have a choice to choose second and third and first and third, but I will use this x square minus y square over here. Okay. Choose any two fractions. Choosing second and third fraction of 1 together, we will have dy upon x, dz upon xy square x square minus y square. See, this is 2, so I will use 2, or dy upon x. Okay, x will cancel out. Okay, dy, in fact y square. Okay, I will use one more step. Dz upon y square c1 by 2, or c1 y square dy minus dz is equal to 0, which gives us c1 y cube by 3 minus z equals c2. This is the one, or your c1. What is c1? Or x square minus y square into y cube by 3 minus z equals c2. This is the solution. So c1 and c2 together gives the complete solution. Fine. Let me take one more question. Dx by 1, dy by minus 2, dz by 3x square sine of y plus 2x. This is 1. Okay, see, choose first two fractions together, we can have a solution. Taking these two fractions, what I will get? Dx by 1, dy by minus 2, or dy plus 2 dx equals 0, which gives y plus 2x equals c1. Okay, now I will use this. See, I cannot choose these two fractions together because I have x over here. If I will choose here, I can put y plus 2x equals c1. That will be sign of some constant. Okay, it will be taken care of. But this x square, 3x square cannot be taken with dy. So I have to choose only first and third fraction together. Now I will not write taking first and third fraction together. I will get dx by 1 dz 3x square sine of c1 by 2. This is 2. Okay, this is y plus, I have used the first solution which I have obtained by using rule 1. So this is 3x square sine c1 dx equal dz, or 3x integrated x cube by 3 cancels out, x cube sine of c1 is y plus 2x minus z equals c2. So if this is 3, I was saying that c1 and c2 together gives the solution, or 2 and 3 together gives us the solution. Fine. So this is how we have to use rule 1 and rule 2. Let me take one more question. See, dx y minus z dy z minus x dz x minus y. This is 1. Okay, can I solve it? Can I take this and this fraction together? No. Can I take this and this fraction together? No. Or can I take this and this fraction together to get a solution? We cannot take. So there should be one more rule which will let us know what is the solution of such type of equations. Okay? Okay. Now rule third. Let me tell you rule third. What is rule third? Rule third. For solving dx by p equal dy by q equal dz by r. This is 1. Now what is rule third? Rule third is that suppose that you are not able to find a solution by using rule 1 and rule 2. Then we use rule 3, that I will be telling you what is rule 3. Or suppose that I am able to find a solution by using rule 1, but I am not able to use that solution. मैंने क्या किया है? I have used y plus 2x. So instead of y plus 2, I have x square minus y square equals c1. I cannot use that. I just now I used x square minus y square equals c1, or x plus y equals c1. Instead of x plus y, if I get x square plus y square equals c1, or x cube minus y cube equals c1, or any other solution which cannot be used. So what should be done? Okay. Suppose, first of all, let me suppose that first solution is possible, but second solution is not possible. There is one method, okay. Or suppose that first solution is possible, and I am not able to use it, so second solution is not possible. And now what to do? Now see what to do. I am using multipliers. Let me use multipliers P1, Q1, R1. I choose multipliers P1, Q1, R1 such that each fraction of 1 is equal to P1 dx. I have multiplied this by P1, this by Q1, Q1 dy plus R1 dz divided by PP1 QQ1 plus R1. This is 2. I have chosen this P1, Q1, R1. Let me tell you, P1, Q1, R1 are functions of x, y, z again. This P, Q, and R, these are functions of x, y, z. I have chosen multipliers P1, Q1, R1, which are also functions of x, y, and z. Okay. I have chosen that they may be constant, that's okay. But they can be functions of x, y, z also. Okay, constant, then it is very easy. I will show you right now. Now I am using P1, Q1, R1. I am multiplying this by P1, this by Q1, this fraction by R1. Then each fraction, I am claiming that each fraction, this fraction is equal to this fraction, this is equal to this fraction, and each fraction, all the three fractions are equal to this. This is ratio proportion, you must have done it. Let me give an example. Suppose I have 1 by 2 equal 2 by 4 equal 3 by 6. If I will choose multipliers, say whatever you like, say 3, 4 and 5, then each fraction, I am claiming that each fraction is equal to 3 into 1, 4 into 2, 8, 5 into 3, 15, 3 into 2, 6, 4 into 4, 16, 5 into 6, 30. What is this now? This is 15 plus 8. How much? 23. 23 plus 3, 26. And this will be 52. 6 plus 6 is 12. 3 plus 1 is 4 plus 1, 52. See, each fraction is 1 by 2. This is 1 by 2. This is 1 by 2. This is 1 by 2. And this is 1 by 2. So this is true. If I have three fractions, I have multiple, choose a multiple, you can choose any multiplier of your own, and you will see that each fraction is equal to this. So this is one thing. I can choose multipliers and I will get, instead of three fractions, I have four fractions now equal. Now comes the method. I can use rule 1. Say I can use this fraction. I can combine this fraction. I have one more fraction. I can combine this fraction with this, or with this to get a solution. Fine? Or if I will get a solution there, I can use that solution to get another solution. This is one method. Or if this is not possible, then I will choose multipliers P1, Q1, R1 such that numerator or denominator is 0. I will choose multipliers P1, Q1, R1 such that, first of all, I have said that each fraction is equal to this. Okay, this is true. Now, I am claiming that I will choose P1, Q1, R1 such that the denominator is 0. And I claim that if the denominator is 0, so is the numerator. How? Let me show you. See, if you have three fractions, alpha by A equal beta by B equal gamma by C equal to K, say, then what is alpha? Alpha is AK, beta is BK, and gamma is CK. Means alpha plus beta plus gamma is K times A plus B plus C. Okay, this is okay. Leave it there. Now, these three fractions are equal. I am choosing a factor. I am choosing multipliers 1, 1, 1 such that each fraction is equal by this method. 1 into alpha, 1 into beta, 1 into gamma, A plus B plus C. And now my claim. If the denominator is 0, so is the numerator. You have seen that. All these fractions are equal and I have got this relation. And if my A plus B plus C is 0, then so is alpha plus beta plus gamma. Okay? So if A plus B plus C means denominator is 0, so is the numerator. Okay? I will be using this now. This is rule 3rd. Okay? Let me explain rule 4th here also. Now suppose that I am not able to find the fraction such that denominator is 0. This can happen. I am not able to find the fraction such, this multiplier such that the denominator is 0. So what will happen? That there comes the rule 4. Rule 4 says that if such is the case, or suppose that I have found multipliers denominator is 0, then so is the numerator. So if this is 0, then I will integrate it and I will get a solution. Okay? I will integrate numerator because numerator is now 0. Means P1 dx, Q1 dy plus R1 dz is 0, which is then integrated, and to get a solution which is known as C1 as usual. Okay, this was one method. And suppose that I have got a solution and I will be using this solution to get another solution. This is method 1. Okay, and suppose that this is not possible. Then I have one thing more. I will choose multipliers P2, Q2, R2 such that each fraction of this is equal to, what will be the fraction? P2 dx, Q2 dy plus R2 dz divided by PP2, QQ2 plus RR2. This can be done. I had first chosen multipliers P1, Q1, R1. Each fraction was equal to this. Now I have chosen fractions this, this and this. Each fraction will be this. You can see it by example I have given. You can choose any set of multipliers and each fraction will be equal. Okay. Now, two methods will arise now. Again, if I have chosen these P2, Q2, R2 such that the denominator is 0, then so is the numerator, which is then integrated to get another solution, C2. Okay. Now it is possible that denominator is not 0. Then what I will do is that I will choose P1, Q1, R1 such that numerator of 2, numerator and denominator, numerator and denominator. I will choose P1, Q1, R1 such that numerator is an exact differential of the denominator. If this is it, see, numerator is dx, denominator is x. Numerator is an exact differential of the denominator. If such is the case, I will integrate it, I will get a solution. Suppose here also, I am choosing P2, Q2, R2 such that numerator is an exact differential of the denominator. Say I have dx plus dy and here I have x plus y. Okay, then this can be integrated. This is log of x plus y, this is log of x to get a solution. Sometimes it is possible that to combine 2 and 3, I will get a solution. If I have got a solution, then I can use that solution to get another solution. Okay, instead of now 3 fractions, we have 4th fraction, we have 5th fraction, we can have 6th fraction also, 7th fraction also. This depends on your intelligence and etc. Okay, now let me take up questions. I hope you understand this. Okay. See, I will take a very simple question. Very, very simple. Say I have taken dx by y, dy by minus x, and say dz upon, okay, 2x minus 3y. This is one. See, dx by p, dy by q, dz by r. Now you can yourself see, I can choose first and two fractions, first and second fraction together. Okay. Choosing first and second fraction together, what I will get? X dx plus y dy equal to 0. I will get dx by y equal dy by minus x, or x dx y dy equal to 0, which gives x square plus y square equal to c1. See, this is a solution. Let me suppose that I am in rule 1. I am using rule 1. I am using rule 1 actually. I am getting a solution, but this solution cannot be used anywhere. So I cannot use this solution to get another solution. So I have to choose something else. So I will be using multipliers. See, you have 2x over here and you have minus x here. So if I will choose 2 here, I will choose 2. Then this will be minus 2x plus 2x. This will be 0. Now I have minus 3y over here. If I will choose 3 here and 1 here. So using or choosing whatever I will write, this is important. You have to write exactly like this. Using 3, 2, 1 means 3 is with first fraction, 2 is with second fraction, 1 is with third fraction. As multipliers, then I will not write, then I will get no. Then this is important. Each fraction of 1 is equal to each fraction is equal to 3 dx plus 2 dy plus 1 dz divided by 3y minus 2x plus 2x minus 3y. I have multiplied this by 3 in the numerator as well as in the denominator. Multiplied this by 2 in the numerator as well as in the denominator. It is not 2 here and minus 2 here. No, I have used, if I will write minus dy by x, remember it, minus dy by x, then I have to write here minus 2 and likewise. Okay. Then I have to choose plus. Wait and watch. If I will choose this as minus, then I have to choose here something else so that this will cancel. Minus 2x and plus 2x will cancel. I have to take minus either in the numerator or in the denominator. I cannot take in both. That's why I have taken here. I have multiplied 2. It will be minus 2 over here. Then see, denominator is 0. And you have seen that when denominator is 0, so is the numerator. Okay, using 3, 2 as multiplier, then each fraction is reduced. Since the denominator is equal to 0, so is the numerator. This is ratio proportion. That is 3 dx plus 2 dy plus dz is equal to 0, which gives us 3x plus 2y plus z equals C2. This is another solution. I have already got the solution C1. This is C2. Say if this is A and this is B, then A and B together gives a solution. Okay, fine. Let me take one more example. Dx upon y minus z, dz upon z minus x minus y, dy upon dx y minus z, dy z minus x, dz x minus y. This is one. See, I cannot take any fraction together. Neither I can, because rule 1 says if you take any two fractions together, then one of the variables should either be absent or it must cancel out. This is not happening. I cannot find solution 1. When I am not getting solution 1, I cannot use rule 2nd. Okay. Now I have to use rule 1. See, if I will using 1, 1, 1 as multipliers, then each fraction of 1 is equal to, this is important, 1 dx, 1 dy, 1 dz divided by y minus z into 1, z minus x into 1, x minus y into 1. What is that? X and x, z and z, y and y. This is 0. Since the denominator is equal to 0, so is the numerator. That is dx plus dy plus dz is equal to 0, which gives us x plus y plus z equals C2 or C1. This was the first solution, C1. This is my first solution. Obviously, I cannot use this solution anymore. I cannot use rule 2. Now, I have to choose one more set of multipliers so that denominator is 0. I will get another solution. Okay. Now, I have taken 1, 1, 1. I cannot take 2, 2, 2, 3, 3, 3, 4, 4, 1. This is not done. Okay. I have to choose something else. So, what I should use? See, if I will use x with this, x times y minus z. See, I will use x, y and z. Let me write. Using x, y and z as multipliers, then each fraction is 1 is equal to, I have chosen x, y and z as multipliers, then each fraction is 1 is equal to x dx, y dy, z dz divided by x times y minus z, y times z minus x, z times x minus y. What is that? This is zx, 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 xy, xy, yz, yz. Okay, denominator is 0. Since denominator is 0, so is the numerator. I will write here, but in next question I will not write. Since the denominator is 0, so is the numerator. That is x dx plus y dy plus z dz equal to 0, which gives us x square by 2 plus y square by 2 plus z square by 2 equals c2. So if that is a and b, gives us solution. Or x plus y plus z equals c1, comma x square plus y square plus z square equals c2. Together gives us the solution. Together gives the solution. Simultaneous equation. Okay. Now let me take this question now. This is x times y times z times. Okay. So what should be the? Obviously, we cannot use rule 1 and rule 2. Okay, I have to use rule 3. I have to show that denominator is 0. So will be the numerator. First of all, this is quite easy. I will use 1, 1 and 1 as multipliers because I have seen that denominator is 0. Using 1, 1 and 1 as multipliers, then each fraction of 1 is equal 1 dx, 1 dy, 1 dz divided by 0. Denominator is 0. Obviously, I have shown you. This gives us x plus y plus z equals c2, c1. This is the first solution. I have chosen 1, 1, 1. What will be another solution? Another solution is quite easy now. You have seen that if x is not here, y is not here, z is not here, it's still 0. Denominator is still 0. So if I will choose 1 by x, 1 by y and 1 by z as multipliers, then each fraction of 1 is equal to dx by x plus dy by y plus dz by z divided by 1 by x into x, y minus z, z minus x, x minus y. So denominator is 0, so is the numerator. Gives log x, log y plus log z equal log of c2. X, y, z equals c2. Okay? Quite easy. Quite simple. You have taken x here, y here, z from here, and you have got denominator 0. When denominator is 0, so is the numerator. Integrate this. This is log of x plus log of y plus log of y equal, this is 0, equals log of c2. So x, y, z equals c2. You will see this method is very much needed in your second semester. So remember it once for all. I have already told you this dx by p, dy by q, dz by r form. You will be using all these 4 rules in your second semester. So remember it once for all. Now let me take one more question. This is y square minus z square, z square minus x square, x square minus y square. So what will you will do? What you will do? So first of all, take x from here, y from here, z from here. Use 1 by x 1 by y, 1 by z as multipliers, then what is each fraction equal to? It is dx by x, dy by y, dz by z divided by. You have taken x over here. From here, this is y square minus z square minus x square minus y square. So this is 0. And you will again get x, y, z equal C1. First solution. Another solution is very important. You choose x, y and z. Okay. Choose x, y, z as multipliers. Then each fraction is equal to x dx, y dy, z dz divided by x square, because you have chosen x, you have chosen y, so y square, z square. So see, this is all 0. Denominator is 0. What you will get as a solution? Numerator is 0, so x square by 2, y square by 2, z square by 2 equals C2. So this and this together gives us the solution. Okay. Next question. This was quite easy, huh? Following it. Okay. Let me take up dx by 1 plus y, dy by 1 plus x, dz upon z. See, this is very simple question. Okay, can you use rule 1? Yes, we can, because I can choose these two fractions. Taking first two fractions together, I will get 1 plus x dx minus 1 plus y dy is equal to 0, which gives us x minus y minus x square by 2 minus y square by 2, x plus x square by 2, y minus y square by 2 equals C1. This is the first solution. Obviously, you are seeing that we cannot use this fraction, this solution anymore. So I cannot be using rule 2. For rule 3, I have to take the denominator is to be put to 0. I have to choose multipliers such that denominator is 0. Your denominator is 1 plus y plus 1 plus x plus z. You see, you cannot make it 0. You cannot choose such things. Okay. So what I will do is, using this is 1, okay, 1 1 1 as multipliers, then each fraction, this is important as I have said, of 1 equals 1 into dx, 1 into dy, 1 into dz upon x plus y plus z plus 2. Right? This is 2. Now what is rule 4? If you have a numerator and denominator such that numerator is an exact differential of the denominator. See, this is x plus y plus z plus 2. What is it? Is derivative? Dx plus dy plus dz. Okay. So numerator is an exact differential of the denominator. Then rule says that you can combine 2 with a suitable fraction of 1 to get a solution. Combining 2 with third fraction of 1, we will get, this is rule 4. If you are not able to find multiplier such that denominator is 0, then you have to choose multiplier such that numerator is an exact differential of the denominator. Then that fraction is to be compared with a suitable fraction of 1, taken with a suitable fraction of 1. So I have taken that, this I will get dx plus dy plus dz by x plus y plus z plus 2 equal dz by z. You see, instead of 3 fractions, you have 4 fractions because each fraction is equal to this. So you have 4 fractions. So in fact, you are taking third and fourth fraction together. This was third fraction, this is fourth fraction. So integrated, you will get log of x plus y plus z plus 2 minus log z equal to log of c2, because c1 I have already found. So you can write it as x plus y plus z plus 2 by z equals c2. This is another solution. So c1 and c2 together gives the complete solution. Okay. Here you are not able to find. You are able to find. You are able to choose rule 1, but you are not able to uh, use that solution. Then you are not also able to use rule 3rd. You are not able to make denominator 0, so that numerator would have been 0. Then rule 4 comes into picture, that you have chosen multiplier such that numerator is an exact differential of the denominator. Next question. It's a very easy question. You will understand this. Dx z plus y, dy x plus z, dz x plus y. In last question, there was one more possibility was there. Let me not discuss it, but there was one more possibility. We could have done something else also. Or let me show that. This was dx upon 1 plus y, right? And dy upon 1 plus x and dz upon z. If I had taken 1, minus 1 and 0, or minus 1, 1 and 0, what I have got? No, I say it easy. d1 minus 1. This is dx minus dy plus 0 dz. And this would have been minus times x minus y. See, 1 plus y minus x, minus 1 and minus x. 1 cancels out, y minus x is x minus y. If I will combine it with this, I will get another solution. This is log of x minus y, this is log of z. Okay? You have to think how to do it. Huh? Now for this, again, you cannot use rule 1. When you are not using rule 1, you cannot use rule 2. And there is no possibility, this is all sum. You cannot have a possibility of you choosing multiplier such that denominator is 0. So what you will do? See how I will do it. Use 1, 1 and 1 as multiplier. Then each fraction of 1 is equal to 1 dx, 1 dy, 1 dz divided by z plus y, x plus z, x plus y. It is twice x plus y plus z. See, this is 2. Now, I have chosen multiplier such that numerator is an exact differential of the denominator. But this one, this 2, cannot be combined with a suitable fraction of 1. In earlier question, we were having dz by z. I was choosing that. But here, I cannot choose it with any of the fractions. So, what I will do, I will choose another set of fractions so that I will get another fraction, so that those two fractions, that fraction can be combined with this. For example, if I will choose 1, minus 1 and 0 as multipliers, 1, minus 1 and 0, what I will get? Dx minus dy and 0, means dx minus dy. Denominator is z plus y minus x minus z. See, choosing 1, minus 1 and 0 as multipliers, I have got dx minus dy, z plus y minus x minus y. Let me choose one more. Choosing this and this, 0, 1 and minus 1 as multipliers, then each fraction is equal to this, which is equal to dy minus dz. I have chosen 0, 1 and minus 1. Okay, this was first one. This is x plus z minus x minus y, And let me choose third one, z minus 1. 1, 0 and minus 1, 0 and z 1. So dz minus dx, x plus y minus z minus y. So this is dx minus dy, x minus y. Okay, dy minus dz, y minus z, dz minus dx, z minus x. This is say 3. Now, instead of these three fractions, you have 4 different fractions, or you have 7 equal fractions. 1 is equal to 2 is equal to 3 is equal to 4 is equal to 5, 6 and 7. You can choose anything. You can choose this and this. We'll get log of x plus y plus z and log of this. This and this, log of this. This and this, or this and this. You need only 2 solutions. Okay? Got it? Next. Dx upon x square, dy upon y square, dz upon z into x plus y. See, this is quite simple question. How will you do this? First 2 fractions you can take. Taking first and second fraction together, you will get x raised power minus 2 dx minus y raised power minus 2 dy is equal to 0. Okay? This is equal to this, means x raised power minus 2. इसको यहाँ ले लीजिए, minus y raised power minus 2. So x raised power minus 1 by minus 1, y raised power minus 1 by minus 1 equals c1. Or, okay, this is one solution. Right? What about another solution? You cannot use this solution now. You cannot use that solution. So what should be the solution? Now let me see. You have x square and this is y square. Let me use 1, minus 1 and 0 as multipliers. Then each fraction is 1 is equal to dx minus dy upon x square minus y square. Or this is dx minus dy x minus y into x plus y. This is 2. Now let me choose 2 or combine 2 with a suitable fraction of 1. This is the method. Combine 2 with a suitable fraction of 1. So let me combine 2 with third fraction of 1. Combining 2 with third fraction of 1. What I will get? Dx minus dy x minus y x plus y equal dz upon z times x plus y. So x plus y goes, this is the numerator, this is exact differentiator. Numerator, exact differentiator. So this is log of x minus y by z equal log of c2. So this gives the solution. Okay? I hope I am able to teach you something, huh? Last one, x square plus y square 2xy dz upon z times x plus y. This is 1. What you will do? 2 or 3 things are there. You can do anything. See, one, if you use first and second fraction, you can have a solution. See, if I use first and second fraction together, I will have dy by dx equal 2xy upon x square plus y square. This is a homogeneous differential equation. Taking first 2 fractions, you can put y equal to vx and solve it. You will get a solution. Okay. Another thing is that you use 1, 1 and 0 as multiplier. What you will get? Dx plus dy x plus y whole square and combine it with this. What you will get? Okay. 1, 1, 0 as multiplied, then each fraction is 1 equal 1 dx, 1 dy, 0 dz, x square plus y square plus 2xy, which is x plus y whole square. Now you are combining this and this, x plus y will go. You will get dx plus dy, x plus y equal dz upon z. You will have another solution. Okay. This is how you will proceed. I will be forwarding questions, more and more questions for your practice only. That will be forward today, inshallah, in the evening. Okay. Bye. Thank you for patient listening. Thank you.